Hi, my name is Elodie Bouzbib and I'm a PhD student at Sorbonne University under the supervision of Gilles Bailly, Sinan Aliou and Pascal Frey. Today's talk will be on the work I've been conducting for my PhD thesis, a robotized tangible user interface for multimodal interactions in VR. In the real life, whenever we want to interact with an object, for instance, this teapot, it's usually done through the object's affordances. For instance, through its base or its handle. Though, when interacting in VR, these bare hands interactions are not available, and we usually have to access an object through a controller and manipulate it by pressing a button. Intuitive interactions, and more specifically bare hands interactions in VR without any contraption of any form, are currently a timely topic, and this is what we investigate in this presentation. In the same regards, more and more haptic solutions are designed to increase interactions intuitiveness in VR while letting the user's hand free of any contraption. These are anchored in the robotic graphics principle. Many robotic graphics mechanical implementations have been proposed in the literature. They can literally display objects using a robotic arm, a drone, or a mobile platform. Or they can reconfigure themselves to simulate an object with tech such as robotic assemblies or 2.5D tabletops or shape-changing devices. We distinguish two categories of robotic graphics. The first one, robotic shape display, consists in displaying a real object of interest. The second one, RoboCells, consists in cellular robots that reconfigure themselves to simulate an object. The keywords in these definitions are reach, dynamically, and desired shape size objects. These tags display themselves and change their configuration based on the user's next intended interactions. In order to use them, they hence need to predict the user's intention to then safely and dynamically reach the virtual object location around the user. In this presentation, I provide a framework towards the enhancement of robotic graphics. First, I propose a solution to control robotic graphics around the user, enabling a safe user navigation. Second, in order to let the users free to choose their interactions, we'll ask how to predict the user's interactions in VR. This anticipation will provide a target position for the interface to reach. Third, I will describe an interface I designed through the different interactions it actually enables. Our solution to control robotic graphics is an accessible, usable, and replicable method on Unity 3D, which enables a safe displacement around users. The first step towards the control of these interfaces is actually to generate trajectories for the interface to follow. These are required to be safe, but also efficient, speed and accuracy-wise. First, let's place ourselves in a VR arena. If we had an object of interest, it's straightforward for the user to actually interact with it. Now, let's add a robotic graphics interface at the bottom right of the arena. The shortest trajectory from the interface's origin to an object of interest would actually collide with the user. So we propose to add a cone-shaped virtual obstacle to the user on Unity 3D physics engine for the interface to avoid it smoothly. In a non-deterministic scenario where multiple objects are equally available, the interface naturally moves at the barycenter of all the objects of interest positions. To do so, it is actually attracted to the different virtual objects with a spring damper model, where their stiffnesses are converted into weights. These weights actually correspond to our second focus, the user's intention. The idea is for the interface to move accordingly with the user's displacements and more precisely, his intentions. Whenever the user is moving, his intentions are changing. To predict which object of interest is about to be interacted with, we propose to calculate a weight per object of interest as a function of the user's orientation and distance to them. For each robotic graphics interface, we provide a simulation where we can tweak and find the relative contribution of the distance over the orientation and test the interface's ability to physically overlay the correct target prior to user interaction. This first model is actually great as to acquire a target prior to interaction in non-deterministic scenario. Though, more generally, bare hands interactions are way more complex than simple target acquisition tasks, and it can't be simplified to gaze, head orientation, or distance. Indeed, grasping is actually task and object dependent. Here, for instance, I'm manipulating this bottle, so it is my object of interest. Though, depending on the task I'm performing, like pushing it, raising it, opening it, I'm not interacting at the same locations over the bottle, so the haptic feedback I'm provided with is quite different. Bare hands interactions such as grasp display challenges. They require multiple contact points over 3D volumes with potentially various shape primitives or depth. They require a much finer accuracy within the object of interest. Therefore, finding out the absolute location of the contact remains quite important to ensure that robotic graphics provide the adequate haptic feedback. We designed a model for predicting users' grasp intention in VR. As an input, we use the user's real hand and base our model from grasp taxonomies. The model is user-independent and adapted for bimanual interactions. As an output, the predictions can be used to extract a shape or primitive from the prediction point vicinity shape-wise and as target positions for the robotic graphics interface to reach position-wise. We extracted 4 features from human reach to grasp behavior and taxonomies: the opposition vector, the grasp direction, the thumb, index, and palm direction, and the grasp depth. We created a geometrical tool to exploit these features: planes. Their orientation are a function of the opposition vector and of the grasp direction. And finally, they're spread over a grasp depth length. They act as cut sections over the objects of interest, and their intersections with the object actually correspond to our predictions. This pipeline breaks down our model in different steps with the user's real hand, and by taking root from taxonomies, we analyzed 4 features, exploited them into cut sections, providing predictions prior to interactions. These predictions can be used with robotic graphics hardware implementations to provide haptic interactions. Now that we know how to safely control the robotic graphics interface and what target it should reach, let's describe CoVR, an example of robotic graphics design, through its hardware implementations and interactions opportunities. Hardware-wise, CoVR is a physical column mounted on a grounded XY Cartesian sailing robot that dynamically overlays multiple virtual objects with only 2 degrees of freedom. It is a robotic shape display. It provides the user with actual physical props, but its mechanical key feature is its large robustness compared to previous works. Software-wise, it obviously responds to the previous algorithm. It predicts which objects to overlay and physically encounters the user at the object of interest position prior to interaction. Interaction-wise, we distinguish 2 main types of interaction with CoVR: when CoVR is static and when it's dynamic. One of CoVR's key features is to have the capacity of resisting to body-scaled user actions such as pushing on rigid walls or leaning on them or crushing under them. And we create interactions on CoVR's panels made of cardboard where users can explore the environment to find a haptic code. On CoVR's skeleton, we can mechanically attach props to enable directed manipulation, replicating, for instance, a slot machine. CoVR can carry multiple potentially heavy objects up to 80 kgs that users can freely manipulate or make interact with each other. For instance, here, the user is freely manipulating a cube that does not fit physically in the locker. For dynamic interactions, CoVR actually provides strong traction forces. For instance, it can act on the users by pulling them and kneading them through forces, but it also enables to literally transport the user. More than that, it also physically initiates the interaction with the user. For instance, here, it's a fabric brushing the user's head. CoVR does not constrain the users to hold continuously a controller as it encounters the user when interaction is required. Whenever it is static, it allows bare hands interaction with over 100 Newton-bursts of stiffness, and through dynamic displacements, CoVR's key feature is to enable whole body interaction with large kinesthetic feedback. To sum it up, I presented a novel framework for robotic graphics interfaces in VR through replicable implementation method and intention models at different scales. Finally, I described CoVR, a robotic graphics interface I designed through its interaction capabilities. Thank you for your attention.